This is joint work with my PhD advisor, Nina Borken, and Li Song, David Wundroff, and Bo Xie. This is about kernel PCA in the distributed setting. So let me first talk about what is kernel PCA. So nowadays we have a lot of complex data such as images, social networks, protein sequences, and things like that. And kernel method is just a systematic way to handle such kind of complex data by using kernel functions to measure the similarities between different data points. We can just use kernel function to measure the similarities between different data points. And we can let the domain experts to choose which kernel function to measure the similarities. And then kernel PCA is just a basic tool based on kernels for extracting nonlinear structures from the data. Mathematically, it's just defined as follows. First, remember that for each kernel, we have a corresponding feature mapping that transforms the original data point to a much higher dimensional kernel feature space. Conceptually, we don't need to work with the feature mapping, but conceptually, the kernel function value is just the inner product in that feature space. And kernel PCA is just to solve PCA in that much higher dimensional feature space. Okay, so the figure shows an example why it's useful. In the original data space, all the data points are close to a nonlinear curve. Suppose after doing the feature mapping, the features lie close to a straight line. If we do one-dimension PCA there, then we can discover this straight line. And went back to the original data space, we discover the nonlinear curve. So this is why kernel PCA can be useful in extracting nonlinear structures in complex data. Unfortunately, for large data sets, it's well known that it's quite expensive to compute kernel PCA. And furthermore, large data sets are usually stored over different machines. We consider the simple master-worker model here. Suppose we have a bunch of worker machines, each have its own local data set, and they can communicate with a central master machine. And then we want to perform kernel PCA over the union of all the local data sets. We emphasize that another challenge is that the data over different worker machines can be from different distributions. For example, the data collecting from one country, like China, can be much different from the data collecting from US. So we are interested in this more general case that the local data sets can be different from each other. So there are some existing heuristics, but all of them doesn't work quite well. The most simple one is just directly send the data points around. Just use the non-distributed algorithm for kernel PCA. But this, of course, leads to high communication because the algorithm itself is not designed for this setting. Another method is just to do subsampling. We can uniformly sample a few data points and then send this subsample to the master machine and then do kernel PCA there. But this often leads to bad solution quality in the sense that if you need a good solution with small error, you need to sample many data points. And that also requires high communication. So a third method is to compute kernel PCA individually on each local data set. You get a bunch of local solutions, and then you average them. But I mean, theoretically, this is only correct when the local data sets are from approximately the same distributions. Finally, there's a more clever way to handle kernel PCA in the distributed setting. You first do a feature approximation in the sense that you approximate the high-dimensional feature mapping by, for example, a random feature or by using Nystrom's method. And then you reduce the problem to distributed linear PCA. This is some distributed linear PCA work, you can just adopt that. However, the problem is that when you do, for example, like the random approximation, random feature approximation, you are not using the prior knowledge that you are going to do rank K principal component analysis. So the approximation is still in high dimension. It's not as high as the original feature, but it's still too high to get low communication cost. So in this work, we just provide a communication efficient algorithm for this problem. It works for, basically we don't assume anything about the local data sets, not assuming they are from the same distribution and things like that. And we have guarantee, or the solution, we guarantee the solution to have error that is within a factor of 1 plus epsilon from the optimal error. And empirically, we also show that the speed up factor scales well with the number of workers. So basically, this is all the design properties we need for distributed kernel PCA. So what's the key idea? I just mentioned that uniform sampling doesn't work. So the first idea is simple. Why do we do weighted sampling? So here, we try to sample according to the importance of the data points. We measure the importance by the notion called statistical leverage scores. This notion is a classical notion in area like linear regression for measuring the importance of the data point with respect to the task. And it turns out it's also useful for PCA. So in our case, it's defined as follows. Suppose we can get all the feature of all the data into one matrix, where each column is just a feature mapping of a data point, as shown in the figure. Now suppose we do a SVD, and the SVD is U times sigma times V transpose. Then the score for the J data point is just the square norm of the corresponding column in V transpose. Okay, so this is just the mathematical definition. But why do we want to use this notion? It seems like it's just abstract math notation. It's because we have this theoretical guarantee. Roughly speaking, it's like, suppose we can compute the scores of the feature mapping, and then we sample a few points according to those scores. Then with good probability, we guarantee that the span of the feature of this sample has a good solution for kernel PCA. So you can imagine that if we can get this score, if we can do the sampling, then we can just project the original data to the span of the feature of this sample, and then we solve the PCA there. So then it would be much easier to solve the problem. Although we still need some other trick, but it would be much easier than the original kernel PCA. But another question is, why this is better than uniform sampling? So here I try to give some intuition by considering a very specific case where we have a cluster of data and then some other data just scattering around this cluster of data. If we do uniform sampling, basically with high probability, with good probability, we just sample the data point from the cluster, right? So we need many sample points to figure out the shape of the data. But what about sampling according to the scores? It turns out that the leverage score has the property that if a bunch of data points cluster together, then each of them would have small score. So it's less likely that we sample from that cluster. And we just need a few sample points to figure out the geometry shape of the data. I mean, there exists theoretical analysis, but yeah, this is the geometry intuition. So as I mentioned, we are going to send around this sample. So a smaller sample immediately means smaller communication. So this is why we want to consider weighted sampling according to these scores. Sounds like a good plan, but unfortunately, computing the scores by definition by SVD is very expensive. So suppose we have n data points, and suppose the feature mapping is finite, like m dimension, then the computation scales with both the number of data points and the dimension of the feature. Furthermore, in our case, we need to do the communication, and then the communication also scale with these two big factors, and it becomes impractical to do so. So here comes our key idea, is just do a technique called kernel subspace embedding to reduce the dimension of the feature. So kernel subspace embedding is a technique we developed. Basically, it's applying random projection kind of technique on the kernel feature to reduce it to very low dimension, like order of k, where k is the number of components we want. So the important thing is that we show if you do that properly, then it's guaranteed that the score after doing kernel subspace embedding can approximate the original score. So we can just work with the data after reducing the dimension. That will reduce the both the communication and computation. However, there's still one issue. We still have a lot of data points, although they are low dimension after embedding, but the number of data points is still large. So we do another subspace embedding. And so to reduce the number of effective points that we need to communicate. So I hide the technical details, but the intuition is that you can do so. You can compute a quantity on the after doing two subspace embedding, and when you reverse back, you can compute the score of the original data points with good accuracy. Okay. So we also know that this subspace embedding can be done locally without introducing extra communication. So you can imagine that after doing this, you reduce the communication and computation significantly. Okay. So here's the summary of our algorithm. In the first step, we just do the subspace embedding, and we send the data, the embedding data to the master, compute the leverage scores there. I mean, you need some other transformation, but at the end of the day, you get a good approximation of the scores. Okay, then you just do the sampling according to the scores. By that I mean you sample a bunch of data points. When you sample one data point, you just pick a certain data point with probability proportion to the score of that data point. I mean, I still hide some technical data here. Actually, only sampling according to the score doesn't work. You still need to add some other extra data points to crack the final sample. But that's not the important issue. We can just do some additional trick to figure out. So the final step is just, as I mentioned, project the original data to the span of the feature of the sample. And then you just compute a solution there. Now it's almost like linear PCA, so you can imagine that you have some other trick to do so. I should point out that here, you cannot just do kernel PCA on the sample points. You must project the original data and then do kernel PCA on that projection. It's because then you cannot guarantee there exists a good solution just on the sample. It's only on the span of the feature of the sample. So you need to do so. Okay, so here's the final guarantee for polynomial kernel. Basically, it means that we get a good solution with communication described here. So it's linear in the number of workers. It's linear in the dimension of the original data point. It's linear in the number of components we want to compute. So all this linear dependence is optimal theoretically, but it depends on the accuracy epsilon is not optimal. The theoretical lower bound on the epsilon is log 1 over epsilon, so there's some space to improve. But the important thing is that the communication is independent of the number of data points, and is also independent of the kernel feature mapping, which you don't want them to appear in the communication bound. Okay, so similar guarantee for some other popular kernels. So, so basically, almost all the useful kernels can be put into this framework. Okay, let me now describe some experiments. First, we compare to some other distributed kernel PCA algorithms on some large data sets. And we compare the performance, compare the approximation error when all the algorithms use the same number of communication costs. So the red curve is our algorithm. The blue one is the algorithm that uniformly sample and then do a distributed algorithm to find out the low rank approximation. The green one is uniform sample and then do a batch kernel PCA on the sample. So the green one is cut short just because batch kernel PCA is very expensive, so we stopped the experiment after like 10 hours. So it's cut short here. So these figures are for the RBF kernel, and we use about 100 workers. And it can be seen that when using the same amount of communication, our method always outperforms the other methods. So this is for polynomial kernel on some data sets. And the same observation is also here, especially for the right-hand side, a large-scale data set, which is like 8 million data points in 100,000 dimensions. Our method is much better than the other existing approach. Okay, we also check how the running time scale with the number of workers. So roughly up to 100 workers, hundreds of workers. If we increase the number of workers by a factor of 4, we decrease the running time by a factor of 2. So roughly linearly. And so this makes it useful for large-scale data sets. Finally, distributed PCA algorithm, kernel PCA algorithm, can also be used as a subroutine for some other downstream applications. So here we consider a form of spectrum clustering, which basically means that you first do kernel PCA, and then you do k-means on the projected data projected onto the principal components you find. So so we perform our distributed kernel PCA algorithm, and then perform distributed k-means from some previous work, and compare to the approach using uniform sampling. So again, we can show that using the same amount of communication, we can get smaller k-means cost at the end of the day. So basically, this is, for more details and experiments, check our paper.
Any questions?
Hi, so is this intuition correct that the reason this works for data from multiple distributions is because the score is invariant to the distribution?
So I think the quick answer to why it works for different distributions is that the whole algorithm is just linear algebra computation. It doesn't make any use of any assumption on the local data sets. Yeah, so you can imagine that it's just like sampling. For example, like sampling, it doesn't depend on how you distribute the data. As long as you have the scores for each data point, no matter where it lies, it gets the same probability to get sampled, right? So it doesn't depend on It's just, yeah. Okay.
So in traditional regression applications, those high leverage points are often a source of spurious results. How does giving them extra weight not fall into the trap of producing a spurious fit?
Yeah, so it's known that PCA can be not so robust to outliers, right? So if you apply this, basically it means that the outlier will have a big effect on the final solution.
Yes.
So one thing is that you can do some truncation, but that's heuristically. If you want some theoretical guarantee, I'm sure that we can also provide some, but I haven't tried that. It's just because like we already have some robust PCA algorithm, right? And analysis. It's based on like similar to truncation of filtering out the outliers.
Yes.
So you can apply the same thing here because after you do projection or for example, like when you compute the scores, you can also do similar thing, like do the truncation or filtering out things. But that messes out the just leads to more technical analysis. So yeah,
Great.
I didn't
Thank you.
perform that. Yeah. Thanks.
Great. Thanks to the speaker again.
Yeah, thanks.